In mid-October, the University of Hawaii's Pan-STARRS-1 telescope discovered an asteroid on its way out of our solar system. The trajectory of the rock and its high velocity showed that it wasn't something from around here. It had come flying in from interstellar space with an origin somewhere in the direction of Vega. It's likely that this asteroid has spent the past several hundred million years alone in deep space, and its chance encounter with our Sun is just a brief one, before it continues its lonely journey across the galaxy. Its discoveries named it Oumuamua. As far as we know, Oumuamua is the first interstellar asteroid we've ever seen, and obviously, it would be amazing if we could somehow go check it out. At the moment, it's out past the orbit of Mars and getting farther away. It's traveling just over 38 kilometers every second, which is stupendously fast, even for space things. Usually, when planning a mission to an asteroid, you'd have plenty of time to plan and prepare, but at this point every second counts, and we're running out of time. A group of researchers from the Initiative for Interstellar Studies I4 published a paper to Arxiv earlier this month taking a preliminary look at some realistic options that we might have for getting a spacecraft near enough to Oumuamua to learn something about it. The good news is that if we act fast, we might be able to get there without inventing warp drive first. For some context, here's a video that NASA JPL put together about Oumuamua, putting aside for now the fact that this thing bears more than a passing resemblance to Rama. You'll notice that Oumuamua has already made a swing around the Sun. Right now, it's pointing about 20 degrees up above the plane of the planets and heading toward the constellation Pegasus. It's approximately 200 million kilometers from Earth. As it heads out of the solar system, it'll slow down a bit to something like 26 km/s. This is significantly faster than any man-made spacecraft. The fastest man-made object is the Voyager 1 spacecraft, which is presently exiting the solar system at 16.6 km/s. It only got going that fast thanks to some carefully planned gravity assist maneuvers around both Jupiter and Saturn, though the fastest spacecraft that we've ever launched was New Horizons, which used a 3-stage Atlas V+5 solid rocket boosters to hit 16.26 km/s as it left Earth. Since we're already late for a Oumuamua rendezvous, we have some catching up to do. And that means a spacecraft that puts both Voyager and New Horizons to shame. Oumuamua will exit the solar system going 26 km/s, so slightly faster than it is the absolute minimum speed that we'd need to hit to catch it, and that's only if we launch something next year and then wait about 20 years for the intercept. Obviously, a 2018 launch isn't realistic at all, and the longer we wait, the worse the numbers get if it takes 5 years to design, construct, and launch a spacecraft. A very aggressive estimate, and we want the intercept to happen within 15 years of launch. Our spacecraft will need to be traveling at around 33 km/s. The figure below shows a range of launch dates and mission durations, with the required velocity to make them work. Note that the lines show excess velocity, how much faster the spacecraft would need to be traveling to intercept Oumuamua. The absolute velocity is an additional 26 km/s, which is the speed of Oumuamua itself. Image Andreas M. Behind this graph shows the required velocities for spacecraft to reach Oumuamua with respect to mission duration and launch date. These high speeds and long mission durations result in several other challenges as well. If it takes your spacecraft a decade or two to catch up to Oumuamua, that rendezvous is going to take place way far away from Earth, probably in the range of 100 to 200 astronomical units. This is about where the Voyager probes are right now, and it's not a particularly friendly environment. It's cold, it's dark, and it takes 10 or 20 hours to communicate one way. Any probe we send out there will need nuclear power, lots of insulation, and an enormous antenna. Also, it's unlikely that a spacecraft we launch in the near future is going to have any way of slowing down once we get it going as fast as it needs to. If you take another look at the figure above, those lines are showing how fast the spacecraft will be traveling relative to Oumuamua at rendezvous. With an excess velocity of something like 10 km/s, the probe will travel the length of the asteroid in about 0.05 seconds, which is not a lot of time for science. Let's be optimistic here and assume that we can put together a spacecraft that'll survive decades in space and do some high-quality science, which brings us back to the big question: can we get it there? The Initiative for Interstellar Studies has a few suggestions for how we might be able to make it happen. The first relies on boring, near-term technologies like enormous chemical rockets. Specifically, hypotheses has come up with a potential mission that uses the space XBFR and on-orbit refueling to send a probe with a bunch of extra engine stages attached to it on an 18-month trip to Jupiter. A gravity assist would then send the probe back toward the Sun, where it would dive down to within 3 solar radii. A maneuver called the solar flyby and fire its engines at perihelion to reach speeds of up to 70 km/s. With a 2025 launch, the space XBFR is supposed to be ready to go in the early 2020s. A spacecraft using this flight profile could reach Oumuamua at just 85 astronomical units in 2039. Or, with a somewhat more gentle profile, a similar mission achieving 40 km/s velocity could intercept at 155 astronomical units in 2051. A slightly more interesting approach that would take a substantial amount of research and development, suggested by hypotheses, is a very small probe propelled by a very large laser. Based on a concept called Project Starshot, the probe would only weigh a few grams, and it would be attached to a reflective sail a few meters in diameter. From the ground, a several megawatt laser beam would be fired at the sail, and the radiation pressure would accelerate the probe at about 1 gram for 3,000 seconds or so, at which point it would be traveling at 55 km/s and take just 7 years to reach Oumuamua. The amount of science that each probe could do would be limited by its very small size, but we could send a bunch of them to compensate. Or we could build a bigger laser to send a bigger spacecraft. Illustration: Adrian Mann. This illustration shows a swarm of reflective sails. Andreas Hein is the lead author on the paper published by the Initiative for Interstellar Studies, and we asked him a few questions about what he thinks we might expect from a near-term mission to Oumuamua IEEE spectrum. With the necessarily political and scientific support, what would your ideal mission to Oumuamua look like? Andreas Hein: the ideal mission would of course reach Oumuamua in no time and return maximum scientific value. Such a mission could be accomplished by a large laser beaming infrastructure such as that proposed by Project Starshot, with a beaming power in the gigawatt range, and a large number of CubeSat-class spacecraft with laser sails, each carrying a different scientific instrument. These CubeSats would use interplanetary CubeSat hardware that is currently under development by NASA. Electric sails that have already been deployed from CubeSats would be used for decelerating the spacecraft when they are reaching Oumuamua. Is it possible to do useful science if the target is passed at a very high velocity? Yes. Such a flyby probe is still capable of doing useful science, as has been repeatedly demonstrated by interplanetary flyby probes such as Voyager, Pioneer, and most recently New Horizons, sending back impressive images from Pluto. Of course, one has to take into account the relatively small size of Oumuamua, which make observations more challenging than in the case of a planet or minor planet. Hence, we have also proposed a few technology options for decelerating the probe, such as an electric and magnetic sail. Both would gradually break the probe, exploiting the deflection of particles from the interstellar medium from the sail. Besides the direct scientific value of visiting an interstellar object, what other longer-term scientific and technological benefits would we gain from attempting a mission like this? First of all, the technology we develop for such a mission would enable various other types of deep space missions, such as the focal mission, where the Sun is turned into a giant gravity lens by placing a spacecraft at a distance of 550 astronomical units, allowing for detailed surface images of exoplanets. Furthermore, a technology such as a laser beaming infrastructure would, once available, allow other applications such as fast interplanetary travel, asteroid deflection, and ultimately interstellar missions. Are you optimistic that an intercept is something we could achieve, or would it be more realistic to view this as an opportunity to prepare for visiting the next interstellar object? We still have about 1 to 2 decades to launch a spacecraft that would reach Oumuamua after 20 to 30 years, given near-term technologies. I'm therefore optimistic that a spacecraft will actually be sent to it. To my knowledge, we can currently only speculate how often such an object enters our solar system and is in addition detectable. Hence, this could mean that if we do not send a spacecraft, we are missing a once-in-a-lifetime opportunity, or maybe even a once-in-a-dozen lifetimes opportunity. According to NASA, an interstellar asteroid similar to Oumuamua might pass through the inner solar system about once per year, although they are very hard to detect, and we have no idea when we'll spot the next one. The Initiative for Interstellar Studies will be taking a look at several mission concepts, and selecting 2 or 3 for more detailed development. You can read the paper in full here. The Heliosp solar probe holds the record for the fastest relative speed ever achieved by a spacecraft at 70.220 km/s. It managed this by flying in an elliptical orbit with a perihelion at only 0.3 astronomical units closer to the Sun than Mercury gets. This means that its orbital energy was much lower, and it wouldn't be able to make it out of the solar system at all. Voyager is much faster in the sense that it has a higher specific orbital energy, which is what matters for catching something exiting the solar system like Oumuamua.